Invited talk by Professor Andrei, and let me read out the introduction for you. Professor Andrei Kovalevsky is a tenured principal researcher at CICECO, Aveiro Institute of Materials, University of Aveiro, Portugal. Currently, he coordinates CICECO Research Line 2, focused on energy and industrial applications. His main research include oxides, thermoelectrics for waste heat conversion, micro and nanostructural engineering of porous ceramics for catalytic and separation applications, design of cost-effective, highly active electrocatalysts for hydrogen and oxygen evolution, and direct electrochemical reduction of metal oxides. Professor Andrei has authored more than 150 scientific research articles with an overall H index of 35 and citation of more than 4,300. He has participated in more than 30 research projects which are supported by European Commission and the Portugal Funding Agency. So with this brief introduction, I would like to invite Professor Andrei to give a talk on specific microstructural effects on the performance of thermoelectric oxides. Professor Andrei, please.
Thank you very much for introducing me. Greetings to from Aveiro to everybody. Although I believe there are many people from Aveiro participating in this conference. Here's our department from Department of Materials and Ceramic Engineering. We are doing our research focused mostly on electroceramics for energy conversion and catalytic applications. Thermoelectrics themselves take a significant part of this research, and today I would like to talk about some microstructural effects in these materials which strongly affect their performance. So here you can see briefly the outline of my talk. I will start with some general introduction of thermoelectrics, and then I have selected some specific cases to discuss, which represent probably not very common situations when we are talking about the microstructural effects on the transport properties. So first I will speak on porosity effects in strontium titanate-based thermoelectrics, and then about some microstructural guidelines to aging mechanism of zinc oxide-based thermoelectrics. So the CBEC effect, which is basically a generation of voltage as a response to the temperature difference, obviously can be used for thermoelectric energy harvesting. So imagine we have material with charge carriers, and when we hit, please take as a very oversimplified view. So when I hit one part of the material, the charge carriers diffuse from the cold side to from the hot side to the cold side, and we have this potential difference. And well, whenever we are able to maintain the temperature difference over our material, we can generate electrical energy in this way. This charging, these potentials are opposite in the case of N and P type materials, so we can then combine them in such kind of couple. And this is a unit of thermoelectric module. And the thermoelectric module looks like this. So it includes a lot of couples shown before. And if you have a heat source, any heat source from one side, and we are able to reject heat from another side, we can generate electrical energy this way. So thermoelectricity, what for? Why? So you should know, of course, that a major part of the energy produced worldwide is actually lost as a waste heat. Of course, CBEC effect could potentially help a lot with recovering at least part of this waste heat. There are many advantages. I will not talk about all of them. Thermoelectric technology, one of those is reliability, which is confirmed by the use of this technology in space missions, Voyager 1 and 2, which are now in interstellar space after more than 40 years of travel. And they have thermoelectric generators, which are working basically on the heat generated by radioactive decay, and they're still operational, and they're still supplying onboard energy. So this is also direct energy conversion. So we're not speaking about any associated greenhouse gas emissions, etc. So the story is very fine, but unfortunately, if we are speaking about efficiency, so we are somewhere here. And if you compare thermoelectrics to those technologies which are alternative, like thermodynamic engines, Rankine or Stirling cycles, they're pretty above thermoelectrics, and even with very optimistic expectations, we cannot come, I think, to this level. Still, the size favors thermoelectric applications, and when I was speaking about applications which require relatively low or intermediate power levels, we can consider thermoelectric technology competitive. So, as I'm speaking about energy conversion, efficiency of this conversion is very important. This is the equation for thermoelectric energy, thermoelectric conversion efficiency. So to have high efficiency, we need to apply a high temperature gradient, and that's why we need materials which are able to withstand high temperatures. And we also need to maximize this so-called ZT parameter, dimensionless figure of merit. And this ZT is basically linked to the very basic material properties as electrical conductivity, CBEC coefficient. CBEC coefficient is basically the ratio between the thermally generated voltage and this temperature difference which generated this voltage, and the thermal conductivity. So actually everything seems quite simple, but the problem is that we cannot have very small window of opportunities to tune these properties independently. So whenever we are, for example, introducing charge carriers to our material, obviously we have an increase in electrical conductivity, but this is accompanied immediately with decrease of the CBEC coefficient and also with an increase of the thermal conductivity. So when we can tune one parameter, but simultaneous changes in other parameters may basically drop off the efficiency itself. So it's very challenging to tune each of these parameters independently. So sometimes we can compare the electrical performances of thermoelectric materials using so-called power factor, which is a product between the electrical conductivity and square the CBEC coefficient. Here you see this nice diagram showing modern concepts for designing thermoelectric material. There are three main aspects, namely structural design, this inner circle, then dimensional design, and finally design of the device. We can use point defects, dislocations, nano-inclusions for band engineering to improve the electrical performance, and also phonon scattering. And this is what we mean under structural design. Then we can involve dimensional design, like producing nanowires, nanocrystals, etc., thin films, super lattices, and finally some bulk material to further improve what we can get with this structural engineering. And finally, device design implies that we need different concepts of thermoelectric modules to get a reasonable output from the structural and dimensional design. You might know that the control of interfaces in thermoelectric materials is crucial for the improvement of the performance. Normally, we are dealing with polycrystalline materials because they are somewhat easier to prepare. Also, in many cases, they have much better mechanical properties. Here, the microstructural alignment, namely preferential orientation, is a very popular approach to improve, to optimize the transport direction. Very popular approach is also to decrease the grain size, relying on the scattering effect on the grain boundaries, which basically scatter the phonons. In this way, you can decrease the thermal conductivity independently on other parameters. We are also not limited to the single-phase materials, of course. You can think about engineering of grain boundaries, where grain boundaries may have different chemical composition from that in the grains and may create some additional benefits. And about inclusion, some non-inclusions, which work very well for thermal conductivity, also in some cases for CBEC coefficient. And finally, we can create some specific microstructure to benefit from those advances already demonstrated for thin film thermoelectric materials, like, for example, addition of graphene, etc. So there is actually a number of pathways to go with microstructural engineering. And regarding oxide, of course, you know that microstructure is decisive in defining their potential, their applications. Oxides are already known as thermoelectric materials as well. In general, ceramic shows probably the broadest range of the electrical conductivity compared to any other type of material. So it covers the range of over 24 orders of magnitude. In transitional metal oxides, the transitional metals themselves, they can have different oxidation states, and this gives rise to different oxide structures, and also different conductivity mechanisms, which can involve the movement of electrons, holes, oxygen ions, and of course some mixed cases. Oxygen itself is a quite widespread element, as you know, and it constitutes a significant part of each oxide. For example, half or more in molar percent, probably less in the weight. There are a number of oxides, quite widespread, but another question is not all of them, they are really suitable for thermoelectric application. And when we are speaking about oxide, we also expect that these materials will be stable in quite a wide range of operation temperatures and operation atmospheres. Here I put some main families of thermoelectric oxides. Actually, a lot of materials were already explored in this sense. Here I put some probably most known, most performing layered cobaltite, reaching quite attractive ZT values, and also these materials probably represent right now the only feasible option for the P-type oxide thermoelectric legs. Perovskites are very versatile, you know, that for different applications and also for thermoelectrics. Here, strontium titanate and calcium manganite are leading zinc oxide-based material, very popular, but they have some inherent drawbacks. I will talk about this later on. And finally, indium oxide-based materials are also interesting, and they demonstrate quite attractive performance. So the first example I wanted to show you regarding the microstructural effect in the case of strontium titanate. So this material represents very promising platform for designing, performing oxide thermoelectrics. It has a very symmetric perovskite structure, which is normally very good for good electrical conductivity. Okay, also there exist a number of possibilities for structural design of this material, creation of different type of vacancies, cationic oxygen, creation of extended defects, etc. And of course, we can further improve this structural flexibility with some microstructural design. Here I just collected from literature some examples of approaches which are being used for strontium titanate, for example, engineering of the grain boundaries. In this case, they contain excessive amount of praseodymium oxide and somehow creates very good conditions for transport of the charge carriers, so the mobility is increasing, and in this way the conductivity is tuned independently from other parameters. Non-inclusions, which work very well for phonon scatterings. Also, you might know that for strontium titanate, we need to use some reducing conditions to prepare this material to trigger reasonable electrical performance. But meanwhile, it also creates some very interesting possibilities for creation such kind of dispersion of metallic particles inside the semiconducting oxide matrix. So it works very well for charge carrier concentration and mobility. So there is also one approach we demonstrated here in our group, such kind of composite containing molybdenum nanoparticles in ceramic bulk, and also some inclusions at atomic scale, which allow to suppress the thermal conductivity and also to enhance the CBEC coefficient due to energy filtering. In fact, another interesting self-nanostructuring approach from our colleagues from Manchester University. So they managed to produce this very nice structures by using specific sintering aid and also applying some specific sintering conditions. Finally, one more very interesting approach of bimodal grain size distribution, where the larger grains create the pathways for electrons, or the charge carriers, electrons in this case, to travel, while the phonons are scattered by the interfaces created by the smaller grains. And another approach is nanoporosity, creation of nanoporosity, which is expected obviously to be beneficial for suppressing the thermal conductivity. Somehow it also affects the CBEC coefficient, although I'm not pretty convinced by the evidence given in this paper. So there is a number of approaches, and well, of course, these are only a few, not all, which are being used. So porosity, this is quite interesting approach, and now porous thermoelectric, they become quite many groups working on that. So idea, by porosity, you can decrease thermal conductivity, but you also decrease in electrical conductivity. It somehow compensate. So you basically have porous material. You can have porous material which has the same performance in the dense. At the same time, you use less material to produce, yeah, and also you produce in lightweight. So the porous, of course, thermoelectric, they have less weight, same material, but being dense. However, for some materials, these porosity effects are not so straightforward. And this is what I wanted to talk in my presentation. So we studied different strontium titanate-based material. And really, a number I showed some interesting effect design, strategy, etc. This is probably less complicated, the approach I would like to talk today. So look at this. So two different examples of tantalum substituted strontium titanate, stoichiometric and containing acide deficiency. And for the major part of the sample, they demonstrate this so-called pseudometallic behavior, which is very good for thermoelectric because it has quite high conductivity value. So these materials have the density range in this, the densities in this range. And the only material which deviates from this, let's say, behavior is the one which has slightly lower density. Of course, it has also high substitution level, and this might be the reason, in particular in this paper, we attributed this behavior to the formation of the extended Rod-Lesden-Popper type defects, which actually block the electronic transport. Well, let's take a look at another example of praseodymium substituted strontium titanate. And again, this behavior is typical for materials which have reasonable density. Reasonable, I mean, for those who want to work with dense materials, so around 90 and above. And again, those two, they have pretty less dense, and you cannot explain this difference by applying any porosity correction formula, whatever, considering any, for example, any composite model where basically the phases are the material itself and voids. So here, what is changing the whole conduction mechanism. So it becomes thermally activated. Well, coincidence, probably. Now let's take a look at another example. Strontium substituted strontium titanate. Again, we have this nice behavior for dense material, and the this thermal activated one for the material which is less dense. So you may ask, you never showed in this slide the material the same, absolutely the same chemical composition and different densities to prove completely that this effect takes place. And unfortunately, I didn't have this this material to show you. And I asked one of my colleagues, Alexei, who works with the same materials but solid oxide fuel cells applications. Unfortunately, he had an example to give me. And so you see, again, the material prepared under the same reducing conditions, but in dense form, shows this pseudometallic behavior, while the material, which is porous, shows the thermally activated type of the behavior. Some guidelines to explain this effects could be obtained from oxygen partial pressure dependence of the total conductivity. Look, so the materials which demonstrate higher conductivity, the dense sample, they also show a negligible oxygen exchange or negligible dependence of the electrical conductivity on the oxygen partial pressure. On the opposite, the porous samples, you see, they show some dependence, and this dependence is not noticeable. So what I think is actually changing the conductivity mechanism is the fact that the open porosity facilitates defects recalibration on cooling from sintering temperature. So what this recalibration actually could involve the consuming of the charge carriers, formation of extended defects. It could be other mechanisms, but the idea is that the pores, you have some specific conditions which facilitate recalibration, and you don't have the frozen high temperature defect structure anymore, while in the case of the dense material, it is still maintained. So if it's oxidation, how it takes place, of course, some advanced methods like the XPS or in situ TM would be helpful, but here we also can get some guidelines from CBEC coefficient portion of it. So the usual tendency, when you have high conductivity, you have lower CBEC coefficient, and vice versa. Here, so the striking observation was that less dense samples, which, as you remember, show also the lower conductivity, they also show the lower CBEC coefficient. And this actually suggests that the grains themselves, they still contain a large amount of the charge carriers, but the charge carrier transport is somehow blocked at the grain boundary. So inside the grains, they're pretty good thermoelectrics, but everything is blocked by the grain boundaries. So, well, the general conclusion here is if you would like to have reasonable electrical performance, strontium titanate-based thermoelectrics, you must densify this material. And this is not because the pore is just a void in conductive matrix. This is because inside this pore, you have some specific oxygen exchange conditions that may even alter the whole charge carrier transport mechanism. Another interesting porosity-related effect on the charge transport we observed in the case of zinc oxide-based materials. So these materials, they have an inherently high thermal conductivity, and this is something very difficult to deal with. But they also show degradation of electrical properties at high temperature, which actually suggests that it's difficult to use them as high temperature thermoelectrics. Here I compiled some examples of aluminum doped zinc oxide with different concentration of dopant prepared by using different routes, and you can see that even for the same dopant content, you can really observe different conductivities, and the values are also dependent a lot on the measurement route. Well, to try to explain what are the relevant effects what could take place in this case, we prepared some model materials containing always fixed amount of the dopant and different dopant, aluminum, iron, zirconium, and at least expectation in the case of iron and aluminum, as the clients having the same oxidation state in good side structure then. Expectation was to have some kind of similar results, but again, you see that electrical conductivity is pretty different. So we have some kind of metallic behavior and also thermal activated behavior. So everything is quite complex, the same with CBEC coefficient. And in the case of the power factor, which is the product of these two, this one and this square, they're also, so the difference appears to be quite minor in terms of the chemical composition, but in terms of performance, the dependence is notable. So all this suggests that these materials can be unstable at high temperature. So we performed here some isothermal measurements versus time to see what is the progress of the evolution of the transfer properties, electrical conductivity, CBEC coefficient, power factor, and these numbers they indicate the changes. And indeed, there are very significant changes, especially in the case of iron-containing samples. So you see at high temperature, especially, the conductivity is notably decreasing, and this is accompanied by simultaneous increase in the CBEC coefficient. And these simultaneous changes actually result in somewhat counterintuitive from the first look. If you look at the power factor, you see that, yes, indeed, in some cases, it decreases with time, which means degradation, etc. That's fine. But in some cases, actually, there is even an increase. We can't speak about degradation in this case anymore. We can speak about improving of the performance. Unfortunately, this effect is somewhat difficult to account in real thermoelectric modules because there the stable operation is one of the main requirements. So what is the relation of this effect to the microstructure? let's take a look at the ceramics before and after electrical measurements. So before electrical measurement, the samples are chemically homogeneous, and after electrical measurements, you can see the formation of significant changes taking place in the pores, namely the formation of aluminium-rich structures, which correspond to the zinc aluminium 2O4 spinel. And these changes are actually much better visible in the case of iron-containing sample, which also showed the highest degradation, as you probably remember. So the sample before, they're chemically homogeneous, and after the measurement, this is a formation of zinc iron spinel, again inside the pores, while the grain boundaries are quite clean. There are no phase impurity segregation at the grain boundaries normally, in most cases. So what is happening is that relatively fast cooling of ceramics after sintering actually avoids any defect segregation because it's relatively fast. So you prepare your material in the furnace, you sinter, you cool down, and the impurity, they don't have time yet to leave, to go out. And also you have some kind of freeze in the high temperature defect structure. Then what happened during the measurement is that oxygen exchange is facilitated in these pores, and here there are also less geometrical restrictions to the formation of new phases. This restriction could take place inside the dense bulk, of course, but here it is somewhat easier for these impurities to leave and to go out. So let's say the microstructural mechanism of high temperature degradation of zinc oxide in zinc oxide based material likely involves the irreversible exsolution of the dopant containing impurities, which is accompanied unfortunately with the consume of the charge carriers. This takes place predominantly in the pores, and well, compared to the previous case of strontium titanate, we were able to show, to demonstrate, to visualize, let's say, this effect, which represent honestly some uncommon effect of porosity on the transport properties. So some general remarks. So basically, with these two examples, I try to show some uncommon porosity-related effects on the performance of thermoelectric oxides. Microstructure may affect indeed the equilibration process, and this could even result in the complete change of the charge transport mechanism. And presence of porosity can also contribute to aging aging process. And whenever we're speaking about, whenever we are thinking about designing porous thermoelectric, which is advantages for some application, we should take into account these possible effects. So some acknowledgement to the projects, and thank you very much for your attention.
Thank you very much, Professor Andrei, for a very nice talk. And now the audience would like to ask a question. Any question?
I can ask one if you want.
Yes, 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 please.
So, as far as understood, in case of iron doped zinc oxide, you also played with the porosity, is correct?
Yeah.
But in this case, it seems that the performance is not very dependent on the porosity, in contrast to the strontium titanate. Is that correct also?
No, actually, we didn't prepare samples with completely different porosities. See, the porosities range are here; they're quite close. So we relied mostly. We didn't compare the samples with, let's say, stepwise change of porosity, but we observed those microstructural changes exactly in the pores, and these microstructural changes, they don't take place in the case of the materials. I mean, you cannot observe this immediately after sintering. But we didn't prepare the material really with different porosity. I probably didn't understand didn't understand well your question. Please tell.
No, actually the question was, yeah, you see here 90 and 99%. So it's quite already 10% difference, yeah.
Yeah, but you see, the question here
our
is
factor is quite the same, for instance.
well, but the question, look, for example, this one has lower conductivity, but at the same time, it shows some kind of metallic behavior. This is the thermally activated behavior. It is not very typical for zinc oxide-based thermoelectrics, let's say, at least for thermoelectric application. And then this material degrades faster than any other.
Okay.
So there are many, I think there are many effects behind, but well.
No, I was trying to compare with strontium titanate.
With strontium titanate, you don't have segregation, direct segregation of impurities. But what I think it takes place, you reoxidase. There is some reoxidation inside the pores. When you cool down, when you sinter strontium titanate based ceramics at high temperature, so then you cool down, yeah, in reducing atmosphere, and if it dense, everything it is not exchanging, and in the bulk everything is compact, everything is fine. But when you have any open porosity, you still have, you can ask where is oxygen in reducing atmosphere? This is a good question. But you may have still some water, and water may act as a oxidizing agent. That's what I think.
I understand. So actually, I just thought, is it the general effect of the pores to all the materials, or it can be related to strontium in one case, in one way, in zinc oxide in another way?
No, yeah, in the case of zinc oxide and strontium titanate, they're not completely similar, but they have some common features. Yeah. For example,
yeah.
if you think about calcium cobaltite, for example, this 349 layered structure, you won't find this porosity effects. So basically, the samples with different porosity most likely will have the difference, which can be then, let's say, attributed only to porosity, only to voids. Okay. And in this case, it is not only voids. It's also some effects which take place inside the voids and through the change the structure of the material.
Okay, thank you.
Thank you.
Okay, thank you very much. And now, Professor Andrei, thank you very much for a very nice talk.
Thank you.
Very wonderful. So somebody would like to ask question? Yes. So if there is no question, we would like to thank Professor Andrei for a very nice and informative talk. Thank you very much, Professor Andrei.
Thank you. Thank you. Thank you.